Imagine trying to perfectly synchronize all the clocks in every city around the world, down to the very millisecond. It sounds like a fascinating challenge, right? Now, scale that idea up to thousands or even millions of computer components spread across vast geographical distances, all needing to agree on what time it is for their operations. This thought experiment quickly reveals a deep complexity. So, why do distributed systems, which relying so heavily on coordination, fundamentally operate without a single, universally agreed upon global clock? The direct answer is that a true, perfectly synchronized global clock in a distributed system is practically impossible to achieve and maintain, primarily due to fundamental limitations in physics and the realities of network communication. Each individual computer or node in a distributed system has its own local clock, but these clocks invariably drift and cannot be kept in perfect lockstep with each other. The core reason lies in a combination of clock drift and network latency. Every physical clock, whether it is on a server or your wrist, is an imperfect instrument. They oscillate at slightly different frequencies, causing them to drift apart over time. Even if you could synchronize them perfectly at one moment, they would almost immediately begin to diverge again. Furthermore, the time it takes for a signal to travel between nodes, known as network latency, is variable and unpredictable. This makes it impossible to know the precise current time of a remote node or to deliver a synchronization signal instantaneously. Imagine trying to set your watch to a remote master clock when the signal itself takes a varying amount of time to reach you. This absence of a perfect global clock means that distributed systems cannot rely on absolute time-to-order events. Instead, they often employ clever techniques to establish a meaningful relative order. One common approach is using logical clocks, like Lamport timestamps or vector clocks. These mechanisms do not measure physical time but assign numerical values to events in a way that preserves causality. If event A happens before event B, then A's logical timestamp will be less than B's. This allows the system to determine the order of operations without needing a global time reference. An interesting detail here is that even Einstein's theory of relativity plays a conceptual role. While not directly applied in everyday system design, it highlights that the very concept of simultaneous events is relative to an observer. In the context of distributed systems, this means that two events occurring on different machines might appear in a different order to different observers, depending on their network position and observation time. This reinforces why a single, absolute timeline is an elusive goal. Understanding that a global clock is not feasible forces engineers to design systems that are resilient to these timing inaccuracies. This leads to the use of powerful distributed consensus algorithms, such as Paxos or Raft, which allow independent nodes to agree on a single value or state, even in the presence of unreliable networks and divergent local clocks. These algorithms ensure data consistency and system reliability by achieving agreement on the order of operations, rather than relying on a shared sense of time. Therefore, the lack of a global clock is not a flaw but a foundational challenge that has driven the innovation of sophisticated algorithms and design patterns. These solutions allow complex distributed systems to function reliably and consistently, ensuring that despite the absence of a universal timepiece, all the moving parts can still agree on what happened and in what order to achieve their intended purpose.
If this helps you code smarter, like, subscribe, and stay tuned for more.